Hi class, today's lesson is on capacitors and a quantity called capacitance. A capacitor is a device that stores charge and essentially it stores electrical energy for later use. It's the earliest form of a battery that was developed. The simplest type of capacitor is called a parallel plate capacitor, where you have two parallel plates that are each charged up with the same amount of charge but a different magnitude. So you have a negative charged plate and a positively charged plate, and they're separated by a distance d. What's special about this parallel plate capacitor is that it forms a uniform electric field. So if we draw the electric field lines within the parallel plate capacitor, then we would draw arrows going from the top plate to the bottom plate, since we know the electric field is always going to go away from positive charges. But it's also uniform inside, so we draw the spacing uniformly. So in a parallel plate capacitor, there's a uniform electric field. Now what this means is that if you were to place a charge at any point in this parallel plate capacitor, so you could place a positive charge up here, or maybe you place the positive charge over here, or you place one down here, then at all of these points, the charge is going to experience some force downward. And that force will be the same everywhere. So the force at, I should label these points A, B, and C. The force at point A is equal to the force at point B is equal to the force at point C. And you can calculate this force by just the charge times the electric field. Now if you place a charge at point A at rest and let it go, since there's a force applied to it, it's going to accelerate down to the bottom plate. If we place a charge at point C and do the same, it will also accelerate down to the bottom plate. But the charge placed at point A has a longer distance to go through, so that force is applied for over a longer distance, which means more work is done, and it will gain more kinetic energy. So a charge at point A is going to have more potential energy, more ability to convert that energy into another form such as kinetic energy, than a charge placed at point B, and that would be larger than the potential energy for a charge placed at point C. This potential energy is also related to quantity we studied last time, which is the electric potential. The electric potential is the amount of potential energy per unit charge. If you remember from last class, we also discussed this concept called an equipotential surface. Equipotential surface was always perpendicular to our electric field, so we can draw the equipotential surfaces in, and inside the parallel plate capacitor, these equipotential surfaces would look like lines that are drawn across. What this is saying is that any charge, again, placed on one of these surfaces at that point, or that point, or that point, will all have the same exact potential energy per unit charge. Since this is a constant electric field, we know that we can calculate the potential difference between the top and bottom plates as the field times the distance between the plates. And if you don't remember how we got this, then take a look at our first lecture where we define the electric potential. Okay, so now let's put one of these capacitors to use inside a circuit. What I've drawn down here is a very simple circuit diagram where you have a point in the circuit that has high potential, so this could be the positive end of a battery, and you have a point in the circuit that has low potential or zero potential, and this could be the negative end of a battery. The difference in potential across the positive end and negative end would just be V minus 0 or V. These lines here represent wires. All wires are drawn with straight lines, and then this guy right here, that's your capacitor, the two parallel plates. Now, if you have some positive charges in these wires, then these positive charges are going to be repelled from the high potential area, and they're going to flow down and they're going to accumulate on these plates. Likewise, the positive charges in the negative end of the wire are going to flow towards the zero potential. They want to reduce their energy if they can. And so they're going to flow that way, leaving the bottom plate effectively negative. When this reaches equilibrium, because this is a metal conductor, then we know that the entire top region has to be at the same electric potential. So the top plate has to be held at potential of plus V, and the bottom plate has to be held at a potential of 0 volts. So now across this parallel plate capacitor, you also have this change in voltage. Now the amount of charge that can be held on a capacitor is proportional to the potential difference that's across the capacitor. The larger the potential difference, the more charges that will build up. And the proportionality constant is given by capital C, where C is known as the capacitance. The capacitance describes the capacity in which these parallel plates will be able to hold charge. You can calculate the capacitance based on a couple of geometric factors. The larger the plate area, the more charge is going to be held on it. The smaller the distance between the plates, the more charge is going to be held on it. And then there's another proportionality constant called epsilon zero. Epsilon zero is known as the permittivity of free space, and it's equal to 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. So we have here a relationship between the charge that can be held on the plates and the electric potential that's applied to the plates, and this quantity C, known as the capacitance. Again, A stands for the area of the plates, and D stands for the distance between the plates, or the separation distance. Now there are a couple ways we can connect these capacitors inside of a circuit. The first way that we'll discuss is connecting capacitors in parallel. So the circuit diagram above this diagram right here, this shows two parallel plate capacitors connected in parallel. Each one has a different capacitance, or each one has the ability to hold a different amount of charge. And what I've defined is that parallel plate capacitor 1 has a larger capacitance than parallel plate capacitor 2, which means that the charge on plate 1 has to be larger than the charge on plate 2. Now in terms of their electric potentials, the top plate is connected to the high potential area, positive V, and at equilibrium, this whole section here, since they're all conductors, they all have to be held at the exact same high potential. So they're all held at positive V. Okay. The bottom plate is all connected to the 0 voltage area, so the bottom plate has to all have the same potential of 0 volts, which means that each plate is going to have a change in voltage, and they're going to be the same for both plates. So delta V1 has to equal delta V2, equals the change in potential that's being applied by the battery. Now what we want to do is reduce the circuit into a simpler circuit where you have one capacitor that's going to have the equivalent capacitance of both of those capacitors combined. The high potential area is going to push charges down onto the bottom plate, whereas the charges in the bottom plate are going to get pushed towards the 0 potential area, leaving the top plate with positive charges and the bottom plate with negative charges. Now, since charge is conserved, the total amount of charge that moves around has to be equal to the charge that accumulates on capacitor 1 plus the charge that's going to accumulate on capacitor 2. Now what we can do is replace the capacitance equations for each of these charges. The charge is equal to the capacitance times the change in potential. So this one is the equivalent capacitance. That's going to be equal to capacitance 1 times the change in potential plus capacitance 2 times the change in potential. Now since all of the changes in voltage are the same, we can cancel those out. And what we're left with is that the equivalent capacitance for capacitors connected in parallel is simply the sum of the individual capacitance. The important thing to remember about capacitors connected in parallel is that each capacitor has this change in voltage, and they're going to be the same across both capacitors. However, the charge on each capacitor is going to be different, and you can tell which one has a larger charge based on the capacitance of the capacitors. Now we're going to look at a scenario that's different, and these are capacitors that are connected in series. Now what you have here are capacitors connected in series, where you have a high voltage area that's at positive V, and connected to that, you have a capacitor, and then another capacitor, and then the low voltage area. What happens in this scenario is that you have the positive charges are going to flow down to this plate, and let's say 4 positive charges end up on the top plate of capacitor 1. This is going to drive away 4 charges down to capacitor 2, because these positive charges don't want to be near each other, leaving the top plate effectively negative. And likewise, the charges on the top plate of capacitor 2 are going to drive away the positive charges that are in the bottom part of the circuit, and these are going to go towards the 0 voltage area, leaving the bottom plate effectively negative with the same amount of charge. What we have here is that the charge on capacitor 1 is equal to the charge on capacitor 2. If you look at the equivalent circuit down below, then what we're saying is that you have some positive charges leaving the high voltage area, and they accumulate on the top plate, and on the bottom plate you're going to have the same amount of charge that's going to be drawn away to the 0 voltage area. So these charges have to be equal to the total charge that's being supplied by the battery. Now in terms of electric potential, there's a change in electric potential, a total change across the terminals of the battery. So you have delta V total. This has to be equal to the change in potential across capacitor 1 plus the change in potential across capacitor 2. Now we're going to use the capacitance equation to figure out what this equivalent capacitance is. So this change in potential can be written as the total charge divided by the equivalent capacitance. This is equal to the charge on plate 1 divided by capacitance 1 plus charge on plate 2 divided by capacitance 2. Since all of the charges are the same, we could cancel those out. So these guys all get canceled out, and we're left with this relationship, 1 over Ceq, the equivalent capacitance, is equal to 1 over capacitance 1 plus 1 over capacitance 2. The important thing to remember about capacitors placed in series is that the charge on each of the plates has to be the same, but the potential differences across each of the plates are going to be different.
But they will also add up to the total voltage from the battery.
All right, and that's it for this lecture. I'll see you guys tomorrow in class.